Okay, so at the end of last topic, we had arrived at the discovery and the confirmation of the existence of the positron. Okay, now truthfully, a physicist named Dirac, who pops up all the time in modern physics, had kind of predicted the existence of the positron before these strange things were popping up in cloud and bubble chambers that we, again, later confirmed to be positrons using that lead plate to see that they were positive but had the exact same mass as an electron. Now, it had kind of been predicted that there might be more types of antiparticles. In fact, there might be an antiparticle for every particle. And so physicists began to search for them with this discovery of this new positron, and we found them, okay? We soon came to understand that every fundamental particle had an antiparticle. Not only that, you can make anti-versions of non-fundamental particles. Like we've said before, put an antiproton and an anti-electron together, you've got antihydrogen. Okay, so here in this table is just kind of a summary. The three that we still kind of considered the fundamental particles, because neutrinos were kind of off to the side at this time still. Okay, so you have the electron, you have the anti-electron, or the positron, right? Proton, P plus, antiproton, P minus. And then for neutral particles, again, like the neutrino or the neutron, you can't put the opposite of zero in there because there is no opposite of zero. So you just put a line over top to indicate that you're talking about the anti-version of this particle. And so suddenly our model of matter had just doubled in the number of particles that fit into it, right? Every particle that we thought we had, we now know that there's a matching antiparticle. So we've just doubled the number of fundamental particles we know. Things are starting to get more complex here in our model of matter. Okay, let's pause and talk about antimatter a little bit here, because you might be saying to yourself, well, where is it? Why is everything I know made up of matter? As we've kind of discussed before, but not at length, when matter meets antimatter, they annihilate each other. The reason why, like a lot of stuff in physics, is both simple and complex. It's actually a relatively simple explanation, but the math, and has to do with the concept called entropy. But essentially, the mass energy contained in a particle and an antiparticle, you could think of it as if that mass energy would rather exist as the energy part than as the mass part. And so when two antiparticles are allowed to exist, well, then all conservation laws can be obeyed while they still go on to become energy in photons. Again, beyond physics 30, but just to not completely hand wave over why they annihilate each other, right? And so we call this process very creatively, we call it matter-antimatter annihilation. So the mass of each particle is released as pure energy in the form of 2 gamma photons. Always 2. Why does it have to be 2? Again, without that, you can't have conservation of momentum. You can picture this here, right? Oh, at the beginning, the net momentum is 0. If only 1 gamma photon is emitted, well, photons only travel in one direction, and they have some momentum, so there's no way for this system's overall momentum to stay at 0. And you might be thinking, well, what if they're not just going straight at each other and the net momentum isn't 0? Why can't the gamma photon just go that way with some momentum? Well, that comes out in the math of special relativity, but this example does kind of give you a feel for why there must always be 2 photons. Okay, so essentially particle, antiparticle creates 2 gamma photons. Now, this hasn't answered the question, why is everything matter and not antimatter, right? Sure, they annihilate each other, but why is there so much matter? Why is there no antimatter? Well, at the beginning of the universe, it's pretty well agreed that equal parts of matter and antimatter were generated, and you would have them annihilating each other. But for whatever reason, way back in the infancy of the universe, the scales tipped in the favor of matter, and matter started to win, and you had way more matter come out until fast forward, we are all made of matter. All of the light matter in our universe anyway is made of regular matter, not antimatter. Dark matter, that's another story. And how did this happen? Well, good question. Okay, that is actually one of the bigger questions being researched in physics today. So maybe I'll be able to ask one of you in 20 years why matter beat out antimatter once you've gone off to research this. Okay, so what physics principles are involved in matter-antimatter annihilation? So you can see we haven't gone that far into it, but you can always fall back on your physics principles, right? Because, well, they're principles, they're fundamental, they underlie everything in physics. So given a process, you should be able to kind of pull out what's going on there. So what's the first one you think of? Well, let's look here. We have 2 massive particles becoming a photon that does not have mass, but it does have energy, right? In fact, how much energy does it have? The same amount that's contained in this mass by E equals mc squared. Well, plus any kinetic energy they have, right? So this is not conservation of mass because we have mass here and none here. It's not conservation of energy because this is going to have more energy than these do, but it is conservation of mass energy. Of course, conservation of momentum, yes, it's in there, okay, but realistically, that's just going to say how it can play out. It's not realistically something that explains how and why it can happen. It's more like when it happens, it will follow the law of conservation of momentum. See what I mean? The difference there? Now, if the question we're talking about directions and all that, then we would start thinking maybe this question is asking us to apply the conservation of momentum, right? But the phenomenon itself, if I just told you, why does this happen? Oh, conservation of momentum. Would you be very satisfied? Probably not, right? Another big one here. What's the charge before? Well, plus one, minus one. After, zero, right? That's kind of a reason why antimatter, matter, and annihilation can even happen. Charge must be conserved. But definitely the big one here is conservation of mass energy. If you only had to pick one, pick that one. How does this process compare to pair production? So remember, pair production, you had a gamma photon come in, interact with the nucleus in some way so that momentum could be conserved, and a positron and electron were produced. In other words, photon to electron and positron. Or there was even the other kind where we had two gamma rays interacting, and their energy was converted to mass, positron and electron. So we did this, right? We went the other way. And now this understanding of antimatter, matter annihilation allowed us to explain those weird tracks that suddenly just disappeared and often appeared and then suddenly disappeared. So what was going on? Let's draw it out. Let's think about it. You could have an electron. Maybe it's not even a free electron, one zipping through and leaving its own trail. Maybe it's just an electron that's in an atom of one of the gases sitting in the bubble or cloud chamber, right? It doesn't even have to be a free electron. You have a positron come in, and it's going to leave a trail because it's a charged high energy particle. So it's leaving a trail. And then it makes contact with an electron, its antiparticle. And so what happens? Annihilation, right? And what leaves? Two gamma photons. And so mass energy has been conserved, charge has been conserved, but what's going to happen to the trail? Suddenly there's no trail, right? Gamma photons do not have a charge. They're high energy for sure, but they don't have a charge. So they're not going to continuously ionize gas as they go, leading to a trail of cloud or a trail of bubbles. So the mysterious disappearing tracks, well, made sense now. Last thing we're going to do here is just kind of take a bit of a review and then a bit of a step forward in our understanding of forces, or as you may more often hear them called, interactions. Okay, so we have our four fundamental interactions. We have the strong force that we have learned binds the nucleus together. Soon enough, we're going to learn it actually does something else as well. Okay, we have the electromagnetic force that binds atoms by holding negatively charged electrons to the oppositely charged positive nucleus, right? Or more generally, the electromagnetic force that just causes forces between charged particles. We have the weak force that, as we very briefly saw, regulates radioactive decay, especially beta decay, right? Positive or negative. That is regulated by the weak force. And we have gravitational force that, yeah, the example here is that it holds the solar system together, but it also holds galaxies together. It also holds planets together, right? Earth is held together because all of that iron congregated in one place and is being held together by its own gravity. So the four fundamental interactions. Why are we bringing this up now in our study of the newest model of matter? Well, in the 1930s, okay, physicists had started to work on what would become the beginnings of quantum field theory, or QFT for short. This is the basis of most of modern particle physics, is this quantum field theory. Okay, so this is ongoing, has been very successful, is what particle physicists still use. Now, don't panic, this is more than what you need to know for physics 30, but it does kind of help to contextualize the stuff that we're going to talk about in a bit here. At its most surface level, if I were to give you the elevator pitch of it, it just refers to particles as excitations of underlying fields. And so what that means is the fields are actually more fundamental than the particles. Yes, the particles are there, but really they're just excitations of a field underneath it. So what this is doing is taking classical theory of fields that we've done, electric fields, gravitational fields, all that, and now it's going to give those a quantum makeover. And one of the results is just that particles are excitations of their underlying fields. Now, an important feature of the theory is the prediction that the four fundamental interactions, gravitational, electromagnetic, weak nuclear, and strong nuclear, all are kind of the result, or they're mediated by these virtual force carrier particles. And those particles just carry out the action that we have come to associate with that force, okay? As a very, very simplified analogy that does start to break apart if you ask too many questions, okay? But on a surface level, it does an okay job of communicating the idea. Imagine you're standing on a frictionless surface. Maybe it's a really slippery ice rink, and you and your friend are throwing a ball back and forth. Okay, well, eventually what's going to happen, as you push the ball, you're going to get pushed back a little bit. As you catch the ball, you're going to get pushed back a little bit, right? Now, you and your friend are not touching each other. You're not actually acting on one another, but you are still repelling each other. How are you doing it? Through the use of this mediating force carrying particle, the ball. This kind of helps to explain this action at a distance that has just been part of classical field theory since, well, forever, right? It's just kind of been accepted that, yes, things can influence each other from a great distance. By quantizing it a bit, we get now this slightly different view where particles are kind of mediating it. So just for a real example, not that way oversimplified one, the force carrier of electromagnetism is the photon. That shouldn't come as a surprise to you, right? What is a photon? Well, it's the particle way of thinking about an electromagnetic wave, right? An electromagnetic wave, the electromagnetic force. That makes sense then that a photon would be the force carrier of that thing. What is a photon? It's just an excitation of the electromagnetic field under quantum field theory. Again, knowing necessarily what that means is not a part of physics 30. And to be honest, a lot of these are conceptual tricks that work, that make great predictions. Physicists aren't sure if it's real, right? At a certain point, that starts to become a meaningless question in a lot of ways. Is it real? So essentially you have, let's say, a photon and an electron. They're attracted towards each other. Why? Well, yes, the electromagnetic force. That's all you ever really will have to say in physics 30. But why do they feel the electromagnetic force? How do they feel it? Quantum field theory suggests that they exchange a virtual photon, and that virtual photon carries the attractive force that they feel. So by exchanging those photons, they feel an attraction toward each other. Same way if you and your friend were now passing off a ball to each other, pulling it towards yourself would pull you a little bit closer to them, and them pulling it away from you would pull you a little bit closer to them. Okay. Now, this particular aspect of quantum field theory, since it deals with electromagnetic forces, is called quantum electrodynamics. And this has been called by many physicists the most successful theory that physics has put forward to date. Take a second and chew on that, okay? The most successful theory put forward to date by anything in physics. Everything you have ever learned. Quantum electrodynamics is widely considered the best we've done so far, okay? It has produced predictions that agree with observations down to 10 significant digits. That's pretty unheard of. It's an incredibly accurate theory. So quantizing the electromagnetic field and thinking of the electromagnetic force as being mediated by these photons seems to be a very good model for the workings of matter in our universe, okay? And so the fact that one of the four fundamental interactions was indeed mediated by some particle, the excitation of the electromagnetic field, led us to get excited and say, well, let's look if there's a particle for the other three fundamental forces. And sure enough, we found three of them so far. We've confirmed their existence. We've observed them. We've seen them. So here's a little summary here. We have the weak force. Happens with something called W or Z bosons. Okay, the electromagnetic force we've seen is mediated by photons. The strong force is going to be mediated by something called the gluon. Again, all of these have been observed. Only one has not, and that is the theoretical graviton. Now, we do have a theory that explains how gravity works. It's called general relativity, and it has to do with the curvature of space-time. General relativity works excellent, very, very well, in ways that countless experiments have confirmed. The only thing is general relativity and quantum field theory can't agree on gravity. You may have heard it said that quantum gravity is the next big hurdle to be jumped in physics. Yeah, because coming up with a quantum explanation for gravity will start to unite these two incredibly accurate theories that up until now fundamentally disagree with each other. Achieving this has been called the theory of everything. And it's not that overdramatic of a name. This theory would pretty much everything that we understand in physics. It would allow it all to fit under one umbrella instead of these little separate umbrellas we've had to work under so far. Okay? So the graviton, no, it has not been observed yet. But these force carrier particles, these fundamental particles, all have, okay? And so you can see the number of fundamental particles is increasing. So we went from protons, electrons, and neutrons, right? Now we know there's neutrinos, there's gluons, there's photons, there's these W and Z bosons. Maybe there's a graviton. Either way, moral of the story, we're getting more fundamental particles, okay? Just a reminder, too, of how these forces act and how strong they are, right? Gravity and electromagnetism, they have an infinite range because they're both proportional to 1 over r squared, right? You can make r really, 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 really big, but 1 over r squared doesn't become 0. It just becomes really small, right? So take two particles with mass, put them on the opposite side of the universe, they will feel a non-zero force towards each other. Two oppositely charged particles, put them across the universe, they will feel a non-zero force towards each other. However, as we talked about last chapter, the weak and the strong nuclear forces, well, they're called nuclear forces for a reason. Not just because they have to do with nuclear processes, but also because they are intranuclear. That means they act within the nucleus. They do hit 0. There's a point where the strong nuclear force and the weak nuclear force actually kind of cease to exist. Okay? So they have a very, very short range, and that's why they don't pop up too much in your day-to-day life, even though they're holding every nucleus in every atom in every molecule in your body together. And then relative strength, we have gravity being the weakest, right? Especially when you go within the nucleus and the other ones are present to compare it to. Yeah, it's nothing pretty much. Then you have the weak force, much, much stronger than the gravitational force, but still a lot weaker than the electromagnetic, which is itself quite a bit weaker than the strong force. All right, so as you can see, we are getting more fundamental particles. Our picture of matter is definitely more complex than just 3 fundamental particles as we started with. If you're looking for practice with this stuff, try the topic 2 section of the practice assignment in the Google Classroom or agenda.